side you have kept we have derived the mass conservation equation in the last class and look for two special cases. One is when the flow is incompressible. Okay. You see that the mass conservation equation, or sometime we will call it continuity equation, has become simply divergence of the velocity is 0. Okay. So, for incompressible flow, we have divergence of the velocity vector is 0 and for steady compressible flow the continuity equation is simply divergence of rho u equal to 0. Okay. See, for the incompressible flow, this divergence of u equal to 0, this holds even when the flow is unsteady. Even when the flow is unsteady, that is, in this case, this u can be function of time. Velocity at a point is a function of time. However, still the time derivative do not appear in the equation, even when the flow is unsteady in case of incompressible flow. That is because of that constant density case. In case of compressible flow, the equation becomes simply a divergence only when the flow is steady. Otherwise, that d rho dt term will be present. So, for compressible flow, this u or this rho is not function of time, they are simply just function of spatial coordinates. Now, the special it is in this case, that is, in both these cases the mass conservation equation is expressed simply as a divergence. In one case it is divergence of the velocity field, and in one case it is divergence of the velocity into the density. Now, let us assume that further another simplification, that the flow is steady. If the flow is two dimensional, let us further assume that the flow is two dimensional, then this divergence is basically sum of two derivatives. So, for 2D flow, this then equation becomes, for 2D flows, in case of incompressible flow, the equation becomes, what do we write, u v w x y or u 1 u 2 x 1 x 2, either way. So, let us write this divergence of u is simply du dx plus dv dy equal to 0. And in case of compressible flow, compressible steady flow, in this case, in both these cases where this divergence can be expressed just simply by sum of two derivatives, it is quite easy to introduce a scalar function, a single scalar function which will satisfy this equation, Say, for the incompressible case, just taking as an example, if for the incompressible case, define it this way. define u as and you see the equation is satisfied. The divergence equation is satisfied. See the simplification. We had two unknown u and v, we have replaced that by a single unknown psi. For compressible case, similarly we can define its little we have to take rho also along with it. See the difference between psi and psi in incompressible flow and psi in compressible flow. In case of compressible flow, the density is also within the definition. In case of incompressible flow, it is not. So, okay. Now, henceforth we will consider the for our further discussion only this incompressible definition, but you can make everything whatever we are doing for incompressible, you can just do the same thing for compressible flow. Wherever there is u, you replace it by rho u, wherever there is v, you replace it by rho v. Okay. So, everything will remain same only with that replacement. This definition suggests that u for incompressible case, now we are whatever we are writing here is for incompressible, u dy minus v dx is an exact differential. And that can be written as delta psi. If you want to make it for compressible, again simply replace u by rho u, v by rho v, that will do, nothing additional. Then integrating it between 2 points within the flow, integrating this equation between 2 points in the flow, say the 2 points we denote by O and P, and the P is the point O x y, say point O and point P. Along any path, along an arbitrary path, let us say this, along an arbitrary path O to P, the integration is carried out. Now, looking to this integration u dy minus b dx, can you say what does it imply? What is the meaning of that integration u dy minus b dx? Imagine a surface of unit depth, that is a surface, or imagine that this line OP is translated by a unit distance in the third direction, the z direction. it will make a surface. If this line OP is translated in the z direction by a unit distance, it will trace a surface of unit width. Think of that surface and then tell what is this, what is the meaning of this integration. U dy, you can think of u z dy, where z is 1. Z dy is then the area, dz dy, but dz is 1 fixed, we have already fixed it. So, 1 into dy become the area of that surface, which is normal to x direction. Okay. So, what is this first term of the integration? Yes, what is the meaning of this? Normal component of the flow velocity into the surface area. What is that? We have already used that term, flux, the volume flux. Okay. So, this is the volume flux. The second term is the same. Yes, second term is again same. This also is dx into 1 z, it is the area normal to this y component. So, this is the flux, volume flux, that is entering through that surface, okay, entering in the generalized sense. It might be leaving, it might be entering. So, this integrand here or this complete integral is simply the volume flux that is entering through the surface traced by this line as it translates unit distance in the z direction. Okay. So, this is the volume flux across, this we will call the volume flux across this line. So, this psi minus psi 0 gives the volume flux across this line. There is a sign convention usually associated with this volume flux. If the flux is counterclockwise with respect to p, then it is taken as positive. If this flux is counterclockwise with respect to point p, then this flux is taken as positive. So, this is the volume flux just to make it short. It is usually not called in this way, that volume flux across the surface formed by translating this line unit, without telling that much, just called that volume flux across this line, where that across that line means that this line is traced in the third direction by unit distance, and then the surface that is formed. So, this is volume flux across the line. Now, think about a pair of paths, two paths that completely make a closed curve. Think about these two paths, let us say. Think about these two paths. This is 1, this is 2, and assume that this is the region that is occupied by these by these closed curve is completely filled with incompressible flow. okay, that this region, this internal region is completely filled by incompressible flow. Then the net volume flux entering across these two paths will sum to 0. That is what our mass conservation equation or continuity equation says, that there will be no rate of extension, no dilatation, no change in volume. So, if this region is entirely filled with incompressible flow and we assume that there is no additional introduction of mass, we are not inserting mass from our volume from outside, like we can have a tube put there and which is discharging there, not doing any sort of things, that there is no volume creation. Then this is by the requirement of the continuity equation, that net volume flux entering this region must be 0. Okay. And what is the, what does it mean then, that this psi, this function is a point function, its value depend only on the location of the point. Because see psi 0, psi minus psi 0 following this path and psi minus psi 0 following this path, they cancel each other. So, that means this psi at this point is simply depends on this point itself, as long as the path enclosing only incompressible flow region. Okay. If the enclosed region is filled with incompressible flow, then this psi has a single value at the point P, or this is a point function. So, this net volume flux is 0, and hence this gives that psi is a point function, and then the difference between the psi between 2 points is simply the value of psi between 2 points, is like psi p minus psi o, that is the way we want. We need only the value of psi at p and at o, it is independent of the path that it follows. Whatever path it may take, the difference will remain the same. Of course, provided the path is one of two paths which completely encloses incompressible flow region, otherwise not. Now then, since the difference of psi between 2 points is given by that integral, what will be the difference of psi when the 2 points lie on a streamline? or what will be the value of psi on a streamline? See, we know the streamline is a line to which the velocity is tangential. Okay. So, what will be the flux across a streamline? 0, because the flow velocity is always tangential to the streamline. So, there is no flux crossing any streamline. So, that means that integrand for the streamline is 0. If that point O to P lies on a streamline, then the integrand is 0. And what does it mean? Psi p is same as psi 0 O, meaning that the function psi is constant on a streamline. Okay. Psi on a streamline is constant. And following this function psi has a special name, it is usually called the stream function. The psi function psi is called a stream function. In this case of incompressible flow, this is a function of position and as well as time. So, psi is basically for incompressible flow case psi x y t, it is a function of position and time. Of course, if the flow is steady, then it is not dependent on t. One thing you must remember that about the function psi, the way we defined this psi and the volume flux we mentioned, it is quite clear that the psi is basically a many valued function, it is not a single valued function. As long as the region is completely occupied by incompressible flow, psi behaves like a single valued function. However, if the region encloses some internal boundary in which there is somehow a creation of volume, maybe like say you have a flow region in which you are introducing some tube which is discharging some fluid there, or also a very simple case, remember that okay, your fluid region is water and think there are some air bubble within it. Then as the air bubble expands or contracts, your incompressible flow region or the water region changes, the volume of the water region changes. Okay. So, in that type of situation where there is some interior boundary in which the volume of the total incompressible fluid can change, then this function is no longer a single valued function. If this rate of discharge or if this rate of increase is m, then every round you make, the value of the stream function will increase by m. So, if you make 2 rounds, it will increase by 2 m, if you make 3 rounds, it will increase by 3 m, and so on. So, however, if that type of situation is not there, there is no internal boundary, or then the function is single valued, but whenever there is an internal boundary, then the function is not single valued. We will later on come back to it and we will see that this needs some special treatment in some of our problems that we will be handling. Now, the stream function and the velocity component in terms of it we have defined for our standard Cartesian system. For other system also you can define it. See, one very useful is the so called polar coordinate r theta coordinate system. Okay. For r theta coordinate system, if you define, again you can define that volume flux exactly in the same manner, and the velocity components, let us say if we call u r in polar coordinates, okay, let us write u r u theta the standard notation. It is 1 by r you can remember, you see that in one case the sign is changing, but it is easy to remember in this way that if you differentiate the stream function by in any direction, you will get the velocity in the direction which is 90 degree clockwise. If you differentiate it any direction, you will get the velocity component in the 90 degree clockwise direction. That is all. You can check it with this, that in both cases that is what it is. If you differentiate it with respect to y, you get the velocity with respect to x, which is 90 degree to the clockwise. If you differentiate it with respect to x, you get the velocity in the negative y direction, which is again 90 degree clockwise with respect to x. So, differentiate by any direction, you get the velocity in the 90 degree clockwise direction. This stream function has another interpretation. If the velocity is expressed as curl of a vector potential, which can always be done, if the velocity is expressed as curl of a vector potential, then the stream function is the third component of that vector potential. That is, if you define curl B, then the stream function is third component is of this vector potential. This B z we are meaning that third component of the vector potential, z component. Also look back to the definition of the streamline, the mathematical expression for stream function, streamline. We did it last class, dx by u equal to dy by v equal to dw by z, sorry dz by w. Forget that third component. For the two dimensional case, it is dx by u equal to dy by v, and you see that that's immediately get that volume flux is 0, u dy minus v dx equal to 0. So, from the definition of the stream function also we can come to it. U dy minus v dx is 0 on a streamline. Any other component, like say if we consider an axisymmetric case or symmetric case in spherical coordinate system, again we can write what are the two components of velocity, and we will do that whenever we come across that type of situation. And now, let us look to something little different, the relative velocity. What exactly the relative velocity leads to in case of fluid motion. So, relative velocity near a point. Let us say we have a point which is denoted by the position vector x, and of course, at time t this is the point P, and let us say at this point the velocity is u. Let us say a neighboring point which position vector is x plus r. Instead of writing any delta x, we are writing r. The distance between 2 points is r, which is of course very small. And again at the same time only, that is the relative velocity at same instant, simultaneous relative velocity. We are not finding the difference in velocity at two different instants. At one point of time, we are seeing what is the difference between the velocity at two neighboring point. And again the velocity will be function of Now, again introducing that vector notation, what is the difference between these two? Or let us say write again this notation. Okay. What will be the difference of this? See, this can be obtained by a Taylor series expansion of this. Okay. This can be obtained as a Taylor series expansion of this. So, this equal to this plus something. So, what is that something? This is the first term of that Taylor series. This equal to this plus this, then plus of course r j square into second derivative of this and so on. But assuming that r j is small to the first order, this is what is required, plus higher order terms, and plus higher order terms which involves square of r j d 2 u I d x j 2, okay, and so on. So, to first order of accuracy we can have only this term. Okay. So, this difference we will call it now delta u. So, the delta u between these 2 points, delta u I is simply r j d u y d x j to first order accuracy. Then look to this term d u y d x j, what it is. See, it has 9 component, d u 1 d x 1, d u 2 d x 2, d u 1 d x 3 and so on, is not it. This d u y d x j, if we expand it, it is d u 2 d x 2 So, d u y d x j is the velocity gradient tensor, it is a tensor, it has 9 component. Gradient of component 1 along direction 1, along direction 2, along direction 3, gradient of component 2 along direction 1, along direction 2, along direction 3. You need 2 quantity to specify it. Gradient of which component and in which gradient in which direction, which component and which gradient in which direction. So, these 2 quantities are to be specified. So, this is a tensor. Velocity gradient tensor. Now, it is a standard rule in matrix that any matrix you can write it as sum of one symmetric and one antisymmetric matrix. If you have any square matrix, you can write it as sum of one symmetric matrix and one antisymmetric matrix. That is always true. You see, this is how that can be done. This d u y d x j can simply be written as half d u y d x j plus d u j d x I plus half d u y d x j minus d u j d x I. And you see, this first part is a symmetric matrix, the second part is antisymmetric. So, that expression for the difference in velocity delta u I can be written as we will call this symmetric part as E I j r j e I j r j xi I j, where the symmetric part we are calling as E I j and the antisymmetric part we are calling as xi I j. And this two part of the velocity difference or two contributions, one by the symmetric tensor, one by the anti-symmetric tensor. We will just call it say symmetric contribution and the anti-symmetric contribution, because you would like to see the nature of each contribution separately. Now, consider first this r j E I j. What is the contribution to this velocity, or what is the nature of this contribution? To understand this contribution, let us say that our axis system is such that, just take it that our axis system is such that it coincides with the principal axis of E I j. Even if it is not, we can orient our axis system so that it coincides with the principal axis of E I j. We can do it. Then of course, there will be no off diagonal term. We are doing it so that we have less number of terms and it is easier to interpret. It is easier to interpret the meaning. That is the only purpose why we want to consider it, that consider the principal axis of E I j, or let us say our axis system is represented by that. Then we have, and let us say that component that coordinate system, just to have a difference, are denoted by prime. Okay. That is, instead of E I j, we will call it E I j prime, when it is the principal system. And we will have then only three component, no off diagonal terms, and this delta u I, the three component are in a very simple form. Okay. And delta u 1 will be, delta u 1 s will be simply r 1 prime E 1 1 prime. This prime is that we are now having the principal system. Okay. Similarly, delta u 2 will be r 2 prime E 2 2 prime, and delta u 3 s will also be R3 prime E33 prime. That is all. In a general case, of course, these are not only one term, there will be other terms also. In this case, delta U1 will be R1 E11 plus R2 E12 plus R3 E13. Delta U1 will be R1 E12 E11 plus R2 E12 plus R3 E13. But now we have only one term R1 prime E11 prime. Also, since this tensor is also have the same invariant, that is EII is same as EII prime. From tensor invariant, EII prime, that is E11 prime plus E22 prime plus E33 prime is same as E11 plus E22 plus E33, that is equal to EII. We have already seen what it is. You can write this explicitly. What is E11 or E11 prime? Look to that expression. What is E11 prime or E11? E11 is simply du1 dx1. Look to the definition of Eij. E11 is du1 dx1. So, this means du1 dx1 plus du2 dx2 plus du3 dx3. This u1, u2, u3 you can replace them u v w, x1, x2, x3 you can write them x, y, z. What is this? Divergence of u. Okay. This is its divergence of u. Divergence of u, and which also we have seen is the same as the rate of dilatation or rate of expansion. So, this is rate of expansion or rate of dilatation, which you have already seen. So, now look to only one component, or imagine the situation, just an imagination. I am not saying that this can happen, that only E11 prime is non-zero, E22 prime, E33 prime they are 0. Then you have only delta U1 which is given as R1 E11 prime. Okay. So, this velocity is simply proportional to the rate of expansion in the same direction. So, each term here represent a motion which is given by the rate of expansion in the same direction. Then think about now a say sphere. Think about now a sphere, and let us say that this motion is given, or this sphere has this motion. The center of the sphere is at x and its circumference is at all those points x r, at x plus r. Now, what will happen to this sphere? That in each principal direction or in each orthogonal direction, it will move by a distance r1 e1. The velocity will be there as r1 e1 in each direction. So, in every 3 major diameter direction, if you take it, each direction is being extended by E11 prime, E22 prime or E33 prime, or let us call it ABC, is being extended at the rate of A, B, C. obviously it will no longer remain a sphere, it will become an ellipsoid. So, this contribution to the motion is such that it will try to make a sphere with which will be an ellipsoid. The element which are on the principal axis, they will not experience any rotation, but simply experience a stretching in the same direction. The other line elements which are not along this direction, they will experience both a stretching as well as rotation, but remember this rotation is such that it is consistent with the stretching along the principal direction. This contribution to the relative motion, or obviously the motion, is called as straining motion. Now, look for the special case. If the flow is incompressible, we know that this is 0, this divergence of u is 0. So, in case of incompressible flow, this motion represent a pure straining motion such that the volume do not change without change in volume. A pure straining motion without change in volume. For incompressible flow, that is the meaning of the term that delta u s, a pure straining motion without change in volume. Of course, if the flow is not incompressible, then there will be change in volume, but in that case again this motion can be decomposed into two parts. One is an isotropic expansion, that is equal expansion in all equal direction given by 1/3 of EII in all equal in all direction, an isotropic expansion, and another straining motion without change in volume. So, this delta u s represent a pure straining motion without change in volume if the flow is incompressible flow. If the flow is not incompressible, then delta u s represent an isotropic expansion plus a pure straining motion without change in volume. So, to summarize, let us write that this delta u y s represents a pure straining motion without change in volume plus for this is only for incompressible flow, only this much. And for compressible flow, an isotropic expansion, that is equal expansion in all direction, Now, let us come to the second contribution, delta u y a, the antisymmetric contribution. What is the meaning of that antisymmetric contribution? What it is? First of all, see that delta u a, by definition, the way we have defined that xi I j, it has only 3 non-zero component. Of course, all diagonal elements are 0. It has only off diagonal elements. That is what is the antisymmetric tensor means, that all diagonal elements are 0, which you can see dui dxj minus duj dxi. So, the diagonal elements will get cancelled. Amongst the off diagonal elements, you see that one is opposite the other, xi 1 2 and xi 2 1. They have same magnitude, but opposite sign. So, basically they have 3 independent value. Xi I j has 3 independent components. So, the xi I j, even though it is tensor, it behaves like a vector, sometimes called a pseudo vector or pseudo tensor. And can be written as xi I j can be written as epsilon I j k omega k. So, that xi 1 2 and xi 2 1 they become opposite sign, same value with opposite sign. So, I think we have to stop here. Xi I j only 3 independent components. Okay, we will stop here today, but you won't be able to complete it today. So, we will continue it. We will continue it next class.